Hello. Today this will be kind of a new thing we're trying out. It'll involve problem solving and, more specifically, evaluating limits, because sometimes we have to do that in calculus. Right, so I like this problem. It's pretty simple, but it involves a clever trick that is pretty common with limits. And in this video, I'll show you all my personal process of evaluating almost every single limit. There's a pretty predictable pattern and some tricks you need to know. All right, so let's begin. We're told to evaluate this limit here of this function, right, as x approaches 2. So the first thing I always do when evaluating limits is just try to plug in this input value to our function, right? So this limit is going to equal, and then we plug in 2 here, 2 squared minus 4, all over 2 minus 2. Now, here's what happens if we evaluate this limit. We get 4 minus 4 over 2 minus 2. And this right here comes out to be 0 over 0, right? Now, this is what we call an indeterminate form. This doesn't really have a meaning that we can discern right now. So if you ever get this, we have more work to do, right? This limit's not over. We are not allowed to say that this equals 0 over 0. This limit does not equal 0 over 0. Let's cross that out. That's not a true statement. All right, so I'm going to rewrite this limit here. Limit as x approaches 2 of x squared minus 4 for x minus 2. All right, so you might have noticed by now that this top numerator here is a difference of squares. So what I'm going to do now is factor out the numerator. This ends up being x minus 2 times x plus 2, right? And if we were to FOIL this out, we'd get this original numerator again. And that is all over x minus 2. Now, before we move on, I'd like to note, every time here that I simplify this limit, we have to still have our limit notation in front of our function, right? This limit notation does not go away until we plug in 2, right? But what I notice here is that we have a x minus 2 in the numerator and an x minus 2 in the denominator. These will cancel out. So this limit ends up equaling the limit as x approaches 2 of just x plus 2. Now if we plug this in, we get 2 plus 2, which just equals 4. And that is a correct answer. We can accept that. Now, graphically, what this looks like, if you were to use a graphing calculator and graph this function right here, it would look like a linear line. However, there's a hole here at x equals 2. Because if we think about what happens with our limit, right, this is a rational function. If we approach 2, as we approach 2 from the left and right side, we figure out that this value, or this limit, just does not exist, or it outputs an indeterminate form as an answer, right? So there's a hole here. The function does not exist at this spot. It exists everywhere else, right? So we can clearly see that this function approaches y equals 4 as we approach x equals 2, right? So now you may be asking, why don't we have a vertical asymptote here? Good question. Ties back to limits. Remember, for vertical asymptotes, if we conduct a limit, let's say x equals 1 for a function, my bad here, this will make it a bit easier, as x approaches 0 of 1 over x, right? Think about what happens as we approach 0, right? What limits are doing is we're, again, getting really, really, really close to 0. So we're 1 over x would look something like this. And that function would have a vertical asymptote, right? Now, as we approach 0, x equals 0 right here, from the left side, we are plugging in very, very, very small but negative numbers for x in our limit evaluation. And so as that negative number gets smaller and smaller, we're going to approach infinity. And from the right side, same thing is going to happen. We are plugging in very, very, very small numbers, but that are positive, right? And so we're going to end up getting a very, very small fraction here. Or my bad. Yes, yeah, very small fraction. Or my bad, yeah, again, sorry, a very, very large fraction. Again, think about plugging in 1 over 0.0001, right? That's going to be a very large number. It's going to extend to infinity. But here, right, as we approach 2, think about this. We're plugging in values such as 1.9, 1.999, and then it keeps going on, right? And then from the right side, 2.1, and then 2.001, 2.0001, and it goes on forever, right? But it ends up being, if you plug in those smaller or closer and closer values to 2, to this function here, we do not shoot out to infinity and negative infinity. So that is why there's no vertical asymptote here. So recognizing this is going to come in handy later. A lot of times we'll be asked to evaluate limits, but we'll be fooled if we say the answer is 0 over 0. We can't say that. We have to factor out sometimes, realize that things cancel, and then come out with a real number for our solution. Other than that, I have nothing else to say. I hope you enjoy. Goodbye, class.